Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we're going to be discussing one-sided hypothesis tests for lambda, where lambda represents the rate parameter of a Poisson process. A gamma prior will be used for the example that we're going to be working on. Let's begin. So, let me show you the example that we're going to be using to illustrate the ideas that are needed to carry out a hypothesis test for this sort of parameter, a rate parameter from a Poisson process using a Bayesian approach. Okay, so this problem was inspired by a situation in an old movie. Okay, the movie is Coma. Okay, anyway, the point is that we have a hospital. Okay, and it turns out that 10 out of the last 30,000 patients, healthy patients, right, went to a coma during routine anesthesias. Okay, so it turns out that back then, when the movie took place, the national average for healthy patients going into comas during routine procedures was 6 out of 100,000, right? So the question is here whether or not 10 out of 30,000 is too high or could be something suspicious when compared to the national average. Okay, so we're going to try to analyze this problem, this situation, using our Bayesian approach. We're going to be considering a gamma prior with these parameters r equals 2, v equals 1, and we're going to carry out a hypothesis test at the 5% significance level. Okay, and then what we are going to, based on our analysis, we're going to try to answer this question, right? If we have evidence that the rate for this particular hospital is too high compared to the national average. Okay, here we go. So let me just be super clear here. What we have, the parameter of interest is lambda, and in this case lambda represents the true rate of patients who go into a coma during routine anesthesia procedure. Okay, at that particular hospital. Okay, at that hospital in question. Okay, we know that the hypothesis test is a 4-step procedure. So step 1, we state our hypothesis. In this case, this is going to be an interesting part of this problem, and that's why I wanted to discuss this one with you. So we're going to have the null and the alternative. Okay, so for the alternative, right? What we want to see is whether or not lambda is greater than the national average, where lambda represents the rate for the hospital in question. And then here, what we're going to have is the complement, right? That lambda is less than or equal to the national average. Okay, but let me go back to our problem here. Note that in this case we have 10 out of 30,000. That's a rate for the hospital, but the national rate is given in terms of 100,000 people. Okay, so they are not in the same units, if you will. And remember that lambda, the parameter of a Poisson process, can be thought of as that, as a rate. Accidents per day, or accidents per week, or defects in a piece of fabric per square meter or per square yard. Okay, so anyway, we have a kind of a particular unit of surface or time, right? And again, it's a rate what we have here. The point being is that these two rates are not in the same units, right? So here we go. Let's think this through, and this is something interesting in this problem. So if the hospital, right, had the same kind of rate, the same rate as the national rate, we could think about this, that number, 6 out of 100,000, as a probability, right, of seeing this particular situation, right? A patient going into a coma during a routine anesthesia, right? Okay, so if you want to find the expected number of people, right, going into a coma during those routine procedures, you have to multiply by the number of people that you're considering. So to find an equivalent rate, what we need is 30,000, which is the number that we're considering here for the hospital, times the national rate. Make sense? So let me write that down here. So it would be 30,000 times 6 over 100,000, right? There we are. And then, right, we are going to have these two rates in the same units, right? And in this case, we are interested in seeing this in terms of 30,000 people, because that's the information that we have for the hospital. Okay, so that rate would be the expected number of patients going into a coma, right, during a routine anesthesia, if, right, the hospital was experiencing the same kind of rate as nationwide. Make sense? Okay, so let me just find that number. In this case, what we have is 30,000 times 6 over 100,000, so 1.8, right? So that turns into a beautiful 1.8. But the interpretation of that 1.8 is that lambda is less than or equal to 1.8 per 30,000, okay? Or lambda is greater than 1.8 per 30,000, because those are the units that we have for the hospital. Our observation is given in terms of that, right? 30,000. Okay? Okay. So, step 1 done. It was a bit interesting to do that, to do the math, so we could compare the national average to the the national rate to the rate that we're observing in the hospital. So we are done with that. Now, step number 2, we have to find our posterior distribution. Okay, so step 2, find posterior distribution. Okay, so first, as usual, we need our likelihood. Our likelihood is going to be a Poisson, right? So probability of observing a particular value for y given a particular value for the parameter lambda, right? So the probability mass function for a Poisson, we know it looks something like this. Lambda to the power y, in this case lambda to the power 10, because what we saw, right, was this 10 out of 30,000, right? So we saw 10 out of 30,000, and then divided by 10 factorial e to the negative lambda, right? Negative lambda. Okay, so that's what we saw here. Great. Now, the other ingredient, of course, is our prior distribution. So remember that in Bayesian statistics we think of our parameter of interest as a random variable, so it has a distribution. So in this case, the distribution that we're going to be considering for lambda is going to be a gamma, right? A gamma with parameters r equals 2 and v equals 1. So that is going to be proportional to lambda to the power 2 minus 1 times e to the power negative lambda v. In this case, v is 1, right? Okay. So that's it, right? That's our prior. We know that our posterior is proportional to the product of likelihood times prior, or prior times likelihood. Likelihood, that's better. Okay, so now in this case, right, our posterior, which could also be expressed as a conditional probability distribution, probability of lambda given our data y, is going to be proportional to this kind of product, right? Remember that we can ignore this 1 over 10 factorial, right? Let me just write this like that. We ignore the normalizing constant, right? This one here, 1 over 10 factorial, that doesn't involve lambda, and we know it's not going to affect the posterior. So once we do the math here, right, this is going to be 12 lambda to the power 12 minus 1 e to the negative 2 times lambda, right? So up to a normalizing constant, right, what we have here is another gamma distribution, which is not surprising because we know that the gamma distribution is the conjugate prior for a Poisson likelihood. Okay, so it turns out that this guy here has a gamma with parameters. The new parameter R star will be 12, and the new parameter V star will be 2, right? Okay, so we have our posterior distribution. We're done with step number 2. Now, step number 3. Step 3 is finding posterior probability of H0. Okay, so probability of H0. We want to find the probability that lambda is less than or equal to 1.8 given our observations, meaning given that now we have this posterior distribution. Okay, so let's find that. Let's just type that what we want is the probability that lambda is less than or equal to 1.8 given what we observed, our data, right? So that just translates into finding the following integral. The integral, we know that gamma distributions are different from 0 in the interval 0 to infinity. But in this case, what we want to do is just integrate from 0 to 1.8, and we know that well, the expression, the PDF that you would use to you know, for our gamma with parameters 12 and 2 would look like this. So first, what we would have is 2 to the power 12 divided by gamma, the gamma function evaluated at 12 times this. Okay, so that's the normalizing constant that we didn't have right before, this guy here. Okay, and we're going to be integrating that with respect to lambda. Make sense? Yeah? Okay. So let me check, is that the right normalizing constant? Yeah, I think it is, but let me quickly check. Yeah, so that's a right normalizing constant. Okay, so now well, doing this kind of integral by hand, I don't expect you to be doing that, okay? Because I mean, you could integrate something that looks like this, integrating by parts, but it would take a while, okay? But there's no need to do that. You guys have access to R, right? And we know that we can easily find that probability using R. Okay, so the function that we're going to be using to find this probability, note that we want the probability up to a point for a gamma distribution. So that's a CDF evaluated at 1.8, right? Okay, so we know that we could use the p gamma function. Okay, we want to evaluate it at 1.8, and the syntax when you want to use that p gamma function is shape will be the r parameter that you have, right, in our case 12, and the rate parameter, the v star, is going to be 2. Okay, so this is what we end up with. So roughly, you know, it would be 3 or maybe close to 4 cases out of 10,000, or 37 out of 100,000, right? So the probability of seeing something like this is really, really small, right? So in this case, we wanted to use a significance level of 5%. Clearly, our posterior distribution is smaller, so much smaller than 5%. Okay, so step number 4, let's reach our conclusion. Since this, our posterior probability of H0 is less than alpha, our significance level, we reject. And let me write down that it's 5%. We reject H0. Now note again that one of the advantages of the Bayesian approach is this is the probability of the null hypothesis, right, is really small, basically 0, really close to 0. So it is not consistent with the national average, right? So what we can say is that we have very strong evidence that the rate of commas at this hospital is unusually high, okay, because the probability of the complement would be the probability of the alternative, right, and that is close to 100%. Okay, so let me just say that we have very strong evidence that the rate of commas at this hospital is unusually high. And that's it. Okay? Okay, so now let's summarize what we did. So we had data with Poisson likelihood. Okay, we know that the parameter of interest when you have a Poisson likelihood is lambda, and one interpretation of lambda is it could be thought of as a rate. Okay, so in this case it was the number of patients that went into a coma during a routine anesthesia at a particular hospital. Okay, so the national rate was 6 out of 100,000, and what we observed was 10 out of 30,000 from our data. So if we wanted to carry out a comparison between the national rate and the hospital's rate, we had to express the rates in the same units. So what we did is we expressed the national rate in terms of 30,000 patients. Okay, so that was the interesting part of stating the hypotheses. And then it was pretty much business as usual. After you have the first step, after you stated your hypothesis, you find your posterior distribution. Just as usual, you combine your likelihood and your prior using Bayes' theorem, right? And in this case, we had a prior that was gamma, so we know that the posterior will also be a member of the gamma distribution family. And then when we want to find the posterior probability of H0, it's so much easier to do this using R. So basically this boils down to evaluating the CDF of gamma distribution. There's a nice function in R, P gamma, that helps you to evaluate the CDF of a gamma distribution. And we just compare that posterior probability of H0 against that significance level, that cutoff. If the posterior probability of H0 is less than the significance level, we reject H0. Okay, and then provide a conclusion in terms of the problem. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.